Hello students, so let us start with a new chapter, that is representative elements. Representative elements. So how can you define a representative elements? Representative elements are the first group, second group, 13th, 14th, 15th, 16th and 17th group of elements that we call representative elements. So these are the elements we can say S block and P block element except noble gases. That's the way you can simply define a representative elements. So let me write first group, second group, third, sorry, not third is not there, sorry. First group, second group, 13th, 14th, 15th, 16th and 17th group of elements. 17th group of elements that we can call representative elements, or these are the elements we can say S and P block elements, S and P block elements except noble gases, we can say are representative elements. So what is S and P block elements? Yes, first and second group. First and second group elements that we call S block element, P block elements, 13th to 18th group that we call P block elements. Okay, so first and second group elements are called S block elements because you can see the final electron are filling in the S orbital. So they simply call S orbital. S block elements. Similarly, in the 13 to 18th group, we will see the final electron are present in the P orbital. So they are P block elements. Now, representative elements means no, the S and P block element except noble gases. Noble gases are not included in the representative elements. Now let us think why it may be. The best reason I can say no, most of the compounds are made out of these elements. That is no first, second, 13th, 14th, 15th, 16th and 17th. Noble gases are unreactive in nature. They have a stable electronic configuration. So generally they do not form compounds. Especially no helium, neon, argon. They are inert in nature. While now most of the compound, if you see, no, you will see these elements are there. Another important point, no, in S and P block element, you will see the outer energy level is incomplete, while inner orbital is no completely filled configuration. That's something no associated with this S and P block elements, where D and F you will see a variability is there between the energy levels. Okay, that we will discuss later. Now for the time being, you understand this is the start of the representative elements. Now let us start by discussing what is the elements present in the S block elements. So S block elements, let me write the first group elements. Remember hydrogen. Hydrogen you cannot include in any group. Hydrogen doesn't belongs to first group element. Hydrogen doesn't belongs to 17th group elements, because hydrogen have the similarity between first group as well as 17th group as well. So you cannot say no hydrogen have a position in a periodic table. It's just included in the first period, not representing any group. So first group element starting with lithium is lithium, sodium, potassium, rubidium, cesium, francium. This is the first group element. Lithium, sodium, potassium, rubidium, cesium, francium. Okay, they are the first group elements. And now this group also called alkali metals. This group also have a name that we call alkali metals. This group is also called alkali metals. Why it's so? Because now you will see they are really reactive in nature. That's the first point you can remember about alkali metals. These are the metals which generally do not see in the free state because of their reactivity. They are now easily combined with oxygen or water. Something that you can remember about sodium, potassium always. They kept in kerosene oil. Why? Because they will react with oxygen, they will react with water as well. So we have to put in somewhere kerosene oil so that no the contact with the oxygen and water is not there. So that will be no, that's the case related to the first group elements. They are highly reactive. Okay, so now why they call alkali metals? Alkali is something related to now the basic property. So first group elements, they combine with the oxygen and water to form oxides and hydroxides, and we will see both are alkaline in nature. The base which can dissolve in water, that we can say alkaline. Okay, some of the bases may not be dissolved in water. So that's the case. We can only say they are basic but not alkaline. But all first group elements, they form easily combine with the water to form hydroxides. They are highly alkaline or strong alkalis, we will say. So that means they are alkali metals. Okay, so that's the first one related to them. And the second one, their reactivity. They are highly reactive metals. They are highly reactive metals, and the reactivity increases from top to bottom. Reactivity increases from lithium to, we will say francium is a radioactive metal. So generally we do not include francium while comparing the properties. So yes, francium is now definitely, if you look at the electronic configuration, there is highly reactive, yes, reactivity is there. But because of no, their half-life is very small, they are not nearly something around 21 minutes or something. So that shows no, they have very little no lifetime. So that why, as we talk about alkali metals, we generally include from lithium to cesium. The reactivity increases from top to bottom. Why? You will get an answer if you look at the electronic configuration. Now similarly, this is the first group elements. Now talk about second group elements. Second group elements. Okay, you have to know about the periodic tables and their elements. That will give you more insight into chemistry. So let us discuss second group elements, starting from beryllium, magnesium, calcium, strontium, barium and radium. Like francium, radium also a radioactive metal, please remember. So now look at here. Here now you will see the first element is beryllium, magnesium, calcium, strontium, barium and radium. Okay, these are we call second group elements. Both first and second group elements are s block elements, because we know s orbital maximum 2 electron can be filled, which means definitely only two group elements we can include in a s block elements. Okay, that's something you will naturally understand if you write the electronic configuration. So next we will write that. So let us discuss about second group elements. Second group elements have another name that we call alkaline earth metals. Alkaline earth metals. The first point, beryllium is not included as an alkaline earth metals. No, it's from magnesium, calcium, strontium, barium and radium, or no, we will call alkaline earth metals. Because no, another case, more the other elements like magnesium to barium, no, they form oxides and hydroxides which are alkaline in nature, and also their metal oxide are found in the earth crust. That why they call alkaline earth metals. But if you check the basic nature of beryllium oxides and beryllium hydroxides, you will see that is amphoteric in nature. It can show both acidic and basic behavior. Okay, and similarly, you will see a dissimilarity in properties by beryllium with respect to other group. Okay, hence now generally beryllium not now we considered as a alkaline earth metals. Anyway, it belongs to this group. While we discussing the property, beryllium is also included. Okay, so that's the point. Their oxides and hydroxides are basic, and also you will see their metal oxides are mainly found in the earth crust. Remember, most of the S block elements never found in earth crust in free state. They wanted to lose electron. They wanted to somehow achieve that stable electronic configuration. We will say stable noble gas configuration. One of the reasons we can say why noble gas do not react, because noble gas have a completely filled electronic configuration or stable electronic configuration. So there is no point of noble gas gaining, losing or sharing of electron to achieve stability. Some elements which is already stable, they doesn't want to lose, gain or share of electron. So that's the point related to the second group elements. They are also reactive. They are also not found in the free states. So this is the general introduction to S block elements. Now let us discuss the electronic configuration. Electronic configuration, let us start with the alkali metals: lithium, sodium, potassium, rubidium, cesium, francium. The electronic configuration I can write with a noble gas configuration and outer electronic configuration. That's the general way we represent now the electronic configuration, because what are the electron present in the inner orbital? No, we doesn't really concern, because chemical reactivity, chemical properties depending on the number of electron present in the outermost energy level. So all we need now how much electron are present in the outermost energy level. That will decide the chemical properties. So generally we write like this. Now the element, the noble gas coming before lithium is actually helium. So we represent with a square brackets. So helium is done. That means 2 electron is done. Lithium having atomic number 3. So one more electron need to be done. So final electron is in the 2s1 energy level. So that's the electronic configuration of, let me write electronic configuration. Electronic configuration. Helium 2s1 is the electronic configuration for sodium. The next noble gas is actually neon and having 3s1 configuration. Potassium after neon, it is argon, so it is 4s1. Rubidium, helium, neon, argon, krypton, 5s1. After krypton, it is xenon, 6s1. After xenon, it is radon, it is 7s1. That's the way the electronic configuration you can write for the first group elements. Remember, we doesn't need the atomic number of every element. Still you can find it. There are methods are there which I will discuss. Anyway, it's all about understanding the outer electronic configuration. So if you have electronic configuration like this, we can easily predict the chemical properties, because you will see in lithium the outer electron are present in the s orbital, that too in the second main energy level. But look at the cesium or francium. Let me compare cesium. The outer electron is present in the sixth main energy level, which means now it's going very much far away from the nucleus. What actually holds the electron inside an atom? It's nothing but nuclear attraction. Nucleus, there is positively charged. A proton is there. That protons always attract the electrons. If the outer electron experience less nuclear attraction, if it experience less nuclear attraction means no, they can either lose no, like no, once the electrons experience, outer electron experience less nuclear attraction, that electron can be removed. So that's related to ionization enthalpy. I will discuss now very shortly. So remember, this electronic configuration tells you lots of stories. So look at here, lithium 2s1. If you compare the outer electron present in the lithium and the outer electron present in the cesium, what's the main difference? You will see the outer electron present in cesium experience very less nuclear attraction, because very much far away from the nucleus. And we will see the in the inner orbital there are so many electrons are there, inner orbitals, and that inner orbital is also contains electron. That electron is also negatively charged, so the inner electron can shield the outer electron. The outer electron may not experience higher nuclear attraction if the inner electron shields the nuclear attraction. So this is just like now, this is my nucleus, this is inner electron. So this inner electron, this nucleus, the outer electron experience less nuclear attraction if this inner electron experience has a good barrier. It can protect the outer electron from the nuclear attraction. So that's the case. Now always you have to think, when you talk about the electronic configuration, it may be similar electronic configuration like every electron present in the s orbital. That doesn't tell the real story. Where it is, now in cesium it is 6s1, in lithium is 2s1. So there is a big difference is there. The 2s electron present in lithium experience high nuclear attraction. Among alkali metals, we have the highest, and now cesium experience very low nuclear attraction. No wonder the reactivity increases down to order, because its reactivity is related to how much, how easily an electron can be released. So I have to say cesium easily releases electron to become cation. Losing an electron, every alkali metal, irrespective, the element, they want to lose electron. This is the tendency of any alkali metals, where Mi can say alkali metals. They wanted to lose electron. That's the point. They wanted to lose electron. So if you compare lithium to cesium, you will see lithium is now experience high nuclear attraction. It will lose electron, but not as easily as cesium is done. So cesium can easily remove electron to become cesium plus to achieve that stable noble gas configuration. So as we move from top to bottom, reactivity increases, because as we move from top to bottom, nuclear attraction experienced by the outer electron is less, which means easily it can remove electron. So that's the point related to lithium and cesium. As we move from top to bottom, you can see the outermost electron is present in the next possible energy level, which means it is second energy level. In lithium, sodium it is 3s1, potassium 4s1, rubidium 5s1, cesium 6s1, francium 7s1. So if you really write this electronic configuration, that almost tells the whole story about the alkali metals. So similarly, let me write the electronic configuration of second group elements, that is beryllium, it will be helium 2s2. That means maximum electron can be filled in this orbital is 2. So you can see it have a completely filled s orbital configuration in beryllium. So after beryllium, it is magnesium having neon 3s2, then calcium, it is argon 4s2. After calcium, beryllium, magnesium, calcium, strontium, it is krypton 5s2, strontium, barium, it is xenon 6s2, finally radium, it is radon 7s2. Here also you will see no radium, which is a radioactive element, so please remember that also generally we do not discuss. So that's all about now second group elements. Look at the electronic configuration. Now it having a 2s2 configuration. Now still the second group elements are highly reactive, because by losing 2 electron it can achieve noble gas configuration. So it has a natural tendency to lose 2 electron. Remember, losing 1 electron doesn't make them stable. If they want to lose, they always likes to lose 2 electron to achieve that stability. Okay, let us write the general way of losing electron. A metal, alkaline earth metal, loses 2 electron to achieve stability. So M can be alkaline earth metals. Alkaline earth metals. Here you will see they likes to lose 2 electron. Okay, by losing 1 doesn't make sense. But here alkali metals, losing 1 electron is enough. Losing 1 electron, they can achieve noble gas configuration. Okay, so this is the important point that related to the electronic configuration. Remember, if you really learn this, that will give you more idea. Okay. Now let us compare the atomic size. Let us compare the atomic size, atomic and ionic size of alkali metals and alkaline earth metals. Here you will see, as we move from top to bottom, atomic size increases. There is no wonder there, because you will see the distance between the nucleus and outer electron always increases as we move from top to bottom, because in cesium the outer electron is present in the 6th main energy level, which means from the nucleus to the 6s1 it is very far. So that is what atomic radius is all about. It's merely the distance between the nucleus to the outermost electron. So definitely atomic size increases. Similarly for alkaline earth metal as well, as we move from top to bottom, atomic size increases. Similarly, if you compare ionic radius, this is the same case. Okay. So, but one point you have to remember. Talk about now the atomic size. Let me write that first point. Atomic size increases from top to bottom. Okay, that's the first one. Now let us think why it's so. Because first point, the outer electron is present in next possible energy level, and inner electron perfectly shields, or we will say screening effect, screens the outer electron. If the inner electrons are good enough to shield the outer electron experiences less nuclear attraction, so the atomic size increases. Remember, if the inner electron do not shields well, If the shielding effect of inner orbital is poor, then now outer electron do experience nuclear attraction, which means no, that will be attracted inwards, which means size will generally decrease. But it's not in the case of a S and P block elements, because now outer electron is experience less nuclear attraction due to the effective shielding of inner orbital electron. Okay, so that's the general case, but in some groups you will see the variation. In some group you will see the irregularity in the variation of atomic size. That's simply due to the poor shielding effect. If you talk about order of shielding effect or screening effect, always s orbital electron shields well compared to p, compared to d, and compared to f. S orbital having a spherically symmetrical shape. That means no, s orbital are very good in the shielding or screening effect. So if the nucleus and the outer electron in which s orbital is coming in between, now s orbital shields really well the outer electron. So something that you can remember, if you see some irregularities in the atomic size as we move from top to bottom, that's simply related to the poor shielding effect of the inner orbital. If d and f orbitals are there, remember they show poor shielding effect or screening effect. Now let us discuss one important point related to this alkali metals and alkaline earth metals. Talk about the compare the atomic size of a cation, that is no, if you compare alkali metals no and the parent metal, if you compare the atomic size of a cation and a parent metal, that means no, let us take an example, sodium. By losing an electron it become Na plus. So I'm just comparing the size of Na plus. By losing one electron, sodium become a cation, and I'm comparing the size of the parent metal, that is sodium. That always you will see the cation having a lower size, very small size. The cation having lower size compared to its parent atom. Why so? Let us think. Let us compare with the sodium. Sodium have 11 electron and 11 proton. 11 electron and 11 proton. Which means no, the nuclear attraction experienced by each electron is no can be almost no, like a equal sharing is there, because 11 electron is there, 11 proton is there. It's remember the protons are attracting the electrons, right? So now think Na plus. What's the case with Na plus? Na plus, the issue is no, it actually lost one electron. So for literally this time 11 proton, and you will see 10 electron. Which means no, number of proton is higher, number of electron is less. So the effective nuclear attraction experienced by the electron increases, because number of proton is higher, number of electron is lesser. Proton attracts, proton is positively charged, right? So the effective nuclear attraction experienced by the electron increases, which means electrons are pulling inwards. So the atomic size always will be smaller compared to the parent atom. So if you compare the size, you can see that very important point. The cations having lower size compared to its parent atom. Okay, now let us compare the alkaline earth metals. What will happen? Alkaline earth metals no is again interesting. This time now it means compare with the magnesium. It become magnesium 2 plus by losing 2 electron. You will see no atomic size again will decrease, because no losing 2 electron means no. So if you compare magnesium, there are 12 proton, 12 electron. Okay. Talk about Mg2 plus, it is having 12 proton and 10 electron. Look at here. Here you will see the effective nuclear attraction again increases. So that's the point. If you talk about cations, no, they are having generally lower size because no, the effective nuclear attraction experienced by the electron increases in the case of cation, so they always attracted inwards, so the atomic size decreases. So let us compare these two ions. If you talk about Na plus, if you talk about, let me compare Na plus, let me compare Mg2 plus, let me compare Al3 plus. What's the specialty here? The specialty is Na plus having 10 electron. After losing 1 electron, sodium become Na plus. Magnesium 2 plus also having 10 electron because again it lost 2 electron. For aluminium again is having 10 electrons. So they have same number of electron, right? So this species we can say isoelectronic species. They are isoelectronic species. Now just compare the atomic size. You will see higher the charge of the cation, size again definitely going to decrease because now we saw Na plus having lower size compared to its parent atom, Mg2 plus having lower size compared to the parent atom. Similarly in the case of aluminium. So you will see if you compare the atomic size, you will see Na plus having the higher atomic size compared to Mg2 plus compared to Al3 plus, where aluminium in the case of Al3 plus the effective nuclear attraction again increases, not as much in the case of Na plus. That's why if you compare among the isoelectronic species among Na plus, Mg2 plus, Al3 plus, you will see Na plus having higher size. It's all about nuclear attraction, how much it is experienced. So that will tell you the story about the atomic and ionic size. Okay, just note down the important points along with the class. Okay. If you want really the datas, let us check Li plus, lithium plus, having a ionic radius or atomic radius, I will say it is 60 picometer, while on the other hand the same element beryllium 2 plus, beryllium 2 plus having a size 31 picometer. Okay, so these are now, if I compare two first elements in their respective group, you will see as we move from, this is the general tendency, as we move from left to right in a periodic table, you will see the atomic size decreases because in a period the main energy levels do not changes. Every electrons are adding in the same principal energy level, so there is no real increase in main energy level. So that's the point. As we move from left to right, atomic size decreases. Now similarly, if you see compare the ionic size also, you will see atomic size decreases. So that's the point related to the atomic and ionic size. The data are given in the textbooks. Please go through to have the values in your mind. Okay. Okay, one more point you can compare, talk about the atomic size among groups. We talk about first group, you talk about second group, as we move from left to right, now up to 18th group. If you think we know from left to right atomic size decreases. So if you compare the among a group, you will see alkali metals having the largest size, compared to any other groups. any other groups. Now let me compare in a particular period. Second period elements are lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. So this is the second group element. As we move from left to right, atomic size decreases. So you will see the highest atomic size in a particular period will be the first element. That's nothing but the first group elements. That is our alkali metals. So first group elements generally represent the highest atomic size in their respective period. In the second period it is lithium, in the third period it is sodium, and it goes on like that. Because now talk about in a period, every electron now present in the second main energy level. This represents the second period, which means now the highest energy level, that is definitely second. So second energy level, now electrons are always now present in the second main energy level, which means now energy level not increase from 2 to 3. So in lithium it is second energy level, neon also in the second main energy level. So as we move from left to right, you will see atomic number increases, number of proton increases, but no, its electrons are not added in the next energy level, which means no, the effective nuclear attraction increases from left to right in a period. That's something associated with every period. That's why we will see from left to right the atomic size decreases. Okay. Okay, let us sum up what we studied today. It is all about now we introduce what is representative elements is all about. It is a S and P block element, except noble gas we call S block element. Sorry, we call representative elements, and you will see the general electronic configuration and atomic size. Please learn this. That will give you a very good idea about the chemical properties. Okay, so keep learning. Now I will discuss the next portion in the next class. Okay, thank you.